All right, guys, I think I'm going to go ahead and get started. Welcome to all of you. I appreciate you being here in person. Couple announcements. It's been like a crazy day for me. It's like the first day of the semester, essentially, except I know it's really the third week. But I've had a lot of people coming by my office, and it's just been a little hectic. Normally, I will get up here a little faster and be ready to go. But I was just a little frazzled there. But yeah, I'm glad you all found your way back to our classroom here. I hope that the first 2 weeks went okay. I know it wasn't perfect to do things through Zoom, but as I mentioned in my Zoom classes, my parents really appreciated having a little extra help for me. And I got their blessing to come back. I flew back over here last night. I got in and actually I had a few people come to my office last night, which was great. If you want to catch me at a less crazy time, that's a really good idea. Come on Monday night, for example. Not too busy. Probably even tonight, especially the later into the evening it gets, things will probably slow down a little bit. My office hour right before this class is kind of a tricky one because I have another class from 1 to 3, and then I have this little break. So you're welcome to come by from 3 to 4, but you might find yourself with a few other people too. I have almost 100 students this semester, so it's a busy time. But anyway, I have lots of availability. Anytime that I'm in my office, you're welcome to talk to me. It's usually the case. I'll leave my door wide open, and you don't have to necessarily restrict yourself to my office hours. The study space that's outside of my room is always open, and that includes pretty much 7 days a week. The only issue is they lock the building at 10 p.m. Now, if I'm in my office at that time and you want to get a hold of me, just shoot me an email. I'll come let you in. It's not a problem. But the security does go through and lock the building at 10 o'clock, but nobody ever gets kicked out of that room that's outside of my office. So you can camp out down there. I'll never forget a few years ago, there was this guy, he was taking Math 350 for like the third time. It's like, I've got to pass this class this semester. And we were and he wasn't in my class, but it was about a week before finals, and I noticed he came in with a whole bunch of groceries, and he had a sleeping bag and stuff. I said, "Are you planning to stay here?" Yes, I'm not leaving this room for the next 2 weeks except to go take a shower. And he was true to that idea, and it worked out, and he passed the class. So anyway, so some people have literally spent 24/7 in there for certain periods of time, but yeah, so that is a nice place that you can hang out. Even if I'm not there, you could be there. And then when I come back, if you've got questions, yeah, I'll definitely try to help you guys out. Um, yeah, a couple other announcements. Today is the last day that you can drop this class without getting a W on your record. So if you're anywhere on the fence about something like that, or you want to talk to me about it before midnight tonight, you can certainly stop by my office hours. I would be happy to discuss that with you, depending on your schedule, how things are going so far, and so on and so forth. Um, so if you just want this to be like it never happened, you've got to do that by today. On the flip side of the coin, today is also the last day that you can add this class without a whole bunch of extra signatures and paying fees for it. There are a few people that are on my waiting list. I am actually going to take attendance today. I just want to make sure that there's a few people. So there's a few people who I added in Canvas because I just wanted you to be able to do the work. But being added into Canvas doesn't mean you're in the class. And I've got a couple people who are emailing me as if they're in the class, and I know for a fact that they're not. So anyway, I will go through my roster in a few minutes, and we'll just make sure that everybody's enrolled. I mean, it should be fine to add people. I think it's not like there's not enough room here, although it's close to being full. Anyway, we do need to get that taken care of today, if possible. As far as the work goes, there is homework due tonight, and during the break today, nobody's put anything up there yet, but that's all right. During the break, if you have any problems from tonight's homework that you think maybe would be good for all of us to look at, I never mind doing some of those problems with you all, and some of them are probably good for everybody to think about. So during the break, you'll have 10 minutes break. We'll give you a chance to write some problems on the side board there. If you haven't done all the problems yet and questions do come up later in the evening, don't forget I do have office hours right after my second class. I don't have office hours right after this class because I have another class, but after 8 o'clock, I would be available both in person and in Zoom. So I'll still do the Zoom office hours if you want to go home. And a couple people came on the other day at like 11:30 at night. That's fine. You can come on Zoom anytime you want, up until midnight tonight, and then just try to get that homework turned in. After this assignment that you're doing for today, there will be another one this week, which will be for Friday. And the one for Friday is going to be the one about Gaussian elimination. I will just warn you that can sometimes be a frustrating assignment because this is the thing where if you make a little sign error in the first step and then you carry it through, you'll have a whole page worth of calculations that may end up having to be scratched, and then you have to start it again. So I would recommend on Friday's assignment that you don't work on that assignment while you're distracted, while you're tired. I would try to pick a time that you can actually focus in on it and be real careful with it. And also just to let you know, I think I said this last week, but just to reiterate that if you make a miscopying error or a sign error on an ERO somewhere in this Gaussian elimination process, it doesn't mean that you're not getting it. It doesn't mean that you don't understand Gaussian elimination. It just means that you're human like the rest of us, like myself, who can occasionally have those kinds of things come up. And you shouldn't take that as a strike against your confidence, right? Because this stuff does get a little bit tedious to do. I tried to assign problems where the numbers shouldn't get too crazy as long as you pick a reasonable series of EROs. We did talk last week, right, about how there's many different correct answers for how you row reduce a matrix. And depending on what choice you made, you could have numbers that are very nice or not so nice. So it's just something to keep in mind. But I tried to pick problems where there's a relatively natural path to the answer that's fairly clean in terms of the numbers and the calculations as well. So anyway, I will take questions on Friday's homework on Thursday. So we got homework due tonight, and then for Friday's assignment, if you start on it in the next couple of days, which you should do, I would not leave Friday's homework until Friday night. So if you stop and look at the homework before Thursday, then you can ask me some questions in class on it as well. So I'll always try to save a little bit of time for that kind of stuff. All right, does anybody have any questions so far? Just kind of getting you oriented here a little bit. All right, well, I will take attendance. I think I'll do that maybe when we take a break here in a little while. I think I'd like to jump in. Yes, question first.
Yeah. So I was just looking at number one for you. That could also be like a scaling correct.
No, permuting is just literally choosing two rows of your matrix and switching them. You're not using any scalars there. Yeah, the scalars comes in on number 2. So nice lead into what I was going to do. I always start my class with a summary of the previous class that I'll put up here. So this is just kind of reminding you from last Thursday. These are the 3 elementary row operations that we talked about. And I just remind you that when you apply these EROs, you don't gain or lose anything in terms of the solutions to your system, right? Nothing is gained or lost. So that's why we have these here, that we're going to use these EROs to perform this Gaussian elimination process here, right? So that we have the permuting operation. We also can multiply a row through by k. K is just some constant, as long as it's not 0. So I don't want you to just zero out a row that way. But any non-zero k can be used as a multiplier that goes all the way through any particular row, right? That's perfectly safe. And then the third one, which does come up a lot, is to add a multiple of one row to another row. And the I and j rows are what are indexed here in this notation. And it's actually the jth row that feels the effect of that ERO, right? So you're using the I throw to actually make a change to the J throw, namely that K times the I throw is being added to the J throw. So it just takes a little practice with these three EROs, and we're going to be practicing this today. Okay. But the idea is to take your linear system. This is the one we started on last Thursday. You take your linear system and you put it into an augmented matrix. I guess I didn't do that yet. We should probably take this system here, put it into an augmented matrix A sharp. And I am, by the way, I am recording this a little bit as best as I can. So we would probably start for the solution by writing down the augmented matrix for it, right? So the A sharp matrix, and I did this last week, so you already probably have this in your notes, but we're just redoing it here briefly to start off today. So I recopy the first set of coefficients from the first equation into the first row, and then I do the same thing on the second row, and then I do the same thing on the third row. Right, so it's gonna look like that. That's your augmented matrix. And every column of this matrix is associated with the unknowns that you have in your system. So here you see I have U, I have B, I have W, I have X, and I have Y. Those are the variables, the unknowns in this system. And our goal is to solve for those unknowns, right? That's going to be the idea. We're going to try to solve for those unknowns. And the process, this is called Gaussian elimination. By the way, this is from section 2.5, which is what we're talking about right here. Basically, we're going to use the EROs to bring that matrix into the so-called row echelon form, right? So I'm going to do these three types of safe operations onto my matrix now and try to get it into row echelon form, okay? Remember that the key thing here is that we're going to have pivots. Those are those things I put diamonds around in the notes last time. Those are the first non-zero entries of each of these rows. And below every one of my, so I can kind of tell already that should end up being a pivot. Now, technically, a pivot should be a 1. That was one of our rules last week. And this is not currently a 1, it's 2. But one way that I could make it a 1 is I could multiply the first row by 1/2. However, if I do that right now, before I've even taken a breath, then I'm going to have fractions in the first row of this matrix that I'm going to have to live with for the rest of all the work I'm going to do. I would prefer not to introduce fractions, and you shouldn't need to do that either on most of the homework problems, at least not until you're like basically done. So I can see that I would like to multiply row 1 by 1/2, but you know what? I'm going to do that at the end. I'm going to do that later. I'm going to save that so that I can keep the fractions out of it for right now. The key thing is that the pivots in the lower rows must be to the right of this pivot. Yeah, and that means that I need to create zeros below this leading 2 right here. So I need to turn this 4 into a 0, and I need to turn this -2 into a 0. And the way you're going to do that is with this third ERO, right? I'm going to add multiples of that first row to those lower rows in such a way that I zero them out. So we actually did it last time, but I'm just reviewing again. I use this little twiddle notation for the EROs. So can somebody tell me or remember from last week? So I'm going to leave the first row the same. Just going to recopy this first. Recopy row 1, yeah, like so. Can somebody remember how did I get a 0 right there last week? What ERO allowed me to obtain that? Sorry? Which, sorry, I need to know like what I and J and all that stuff. You're using the A operation, right? A of what? 1 and 2. We're playing with rows 1 and 2. And what multiple of the first row do I need to add to the second row? -2. -2. So just -2. That's it, right? And to figure that out, I'm only looking at these two numbers. What's happening in the other columns to the right, we're just going to live with whatever happens, right? We're not using that to make any decisions. The decision is all coming from just this comparison right here. -2 times the first row, when it gets added to the second row, zeroes out that 4. Right, but I have to go all the way across the whole first row. I'm doing this mentally. I'm not writing it all down. I'm taking -2 times the first row in my head and adding it to the second row. Yeah, so in this case, -3 times -2, which is 6. I add that to -6, it gives me another 0, right? 1 times -2, I add that to 2, it actually also gives me a 0, right? I just keep going like that. -1 times -2, that's 2, but I add that to -3. 2 plus -3 is -1, right? The next one I have 1 times -2. I add that to -1. That all adds up to -3, right? Doing most of this in my head. 0 times, well, anything is 0. I add that to -5 and I get -5. So there's your second row. I'll go ahead and circle what will ultimately be my pivot that goes with that row, because that's the first non-zero entry in the second row. Okay, and then I have to do the same thing in the third row as well. So what ERO can I use to get a 0 right here in the lower left corner of the matrix?
So, for the pivot, can it be negative then?
No. No, it has to be a 1, so I'm not really done yet.
Okay.
Same reason I'm not done here. I will have to fix that later. Yeah, I will fix that later. Anybody want to tell me what's the other ERO? I'm doing it at the same time just to save writing, and you guys should do that too. A13, thank you. A13 of 1. Right, so I'm going to add row 1 to row 3. You see that? 2 and -2. I want to get this 2 to cancel out this -2. Well, that happens if I add, right? So 2 plus -2 gives me a 0, and I'm going to do the same thing all the way across every column. -3 plus 3 is 0. 1 plus -2 is -1. -1 plus 2 is 1. 1 plus -2 is 0. And 0 plus 3 is 3. All right, and of course here I would have a pivot right there if we were calling that a pivot, but it's not technically a pivot yet. From here, I need to get the pivots in the right order. So I would suggest that we permute rows 2 and 3. And I'll leave everything else the same for a moment. So the first row, I'm not going to change that one, but I'm going to take the third row and put it second. Okay, and then I'm going to take the second row and put it third. Just recopying it, just swapping the second and third rows. Okay, now finally, I'm going to make those pivots into 1s. And this is where I can use that second ERO, which says multiply a row by a constant. So you're just going to basically multiply by whatever reciprocals of these leading values you have, and multiply them through those rows. So I'm going to multiply row 1 by a half. I'm going to multiply row 2 by a minus sign. And I'm going to multiply row 3 by a minus sign. I'm going to do all of this in one step as well. Okay, so this is going to be the last step. So when I multiply the first row by a half, yeah, now I do get fractions, but I saved myself until the very end before I have to have fractions to think about. So this is a okay time to do that. The second row is really just going to pick up a minus sign. And the third row is being multiplied also by a minus sign. So you're just changing the signs on the second and third row. And that should be what we have. I'm going to go ahead and circle my pivots again, like so. Now remember that these 5 columns are lined up with my 5 unknowns. That is still true here. That is still true here. I have U, V, W, X, and Y lined up with those 5 columns. And actually, if we wanted, we could take this new matrix, this row echelon form matrix, and we could write down a corresponding system again. So I could go, I started with a system of equations, converted it to a matrix, then I did a bunch of EROs, and now I go back and write it as a system again, right? I could go back. I could say, oh, this is U minus 3/2 V plus 1/2 W minus 1/2 X plus 1/2 Y, that still equals to 0, right? And then the second row would be W minus X equals -3. And then the bottom row would be x plus 3y equals to 5, right? And this system, now you can kind of see some of the variables here, the u, the w, and the x are corresponding to those pivot positions. Now, if you remember from last Thursday, guys, what I said was that doing all of these EROs, we do not gain or lose any solution. So the solutions to our original problem right here is no different than the solutions to this system. Somehow this is supposed to be easier. This is why we went to all this trouble. We did this whole row echelon form reduction process because of a reason, which is that we would like this to now hopefully be easier. What was the phrasing I used? To solve it by back substitution. You remember that one, right? So I'm going to do that. I'm going to now solve this by back substitution, but I actually want to just put a couple of definitions into the notes for you here so that I can speak about the terminology a little bit as I'm doing it. So you see the variables, the u, the w, and the x. Those are called the leading variables at the end of this row echelon reduction process. So the leading variables, and in this example, so I'll just put example here kind of inside my definition here. U, W, and X, those would be the leading variables, right? The leading variables correspond to the pivots. Okay, so that's always, if I talk about leading variables, those are just the variables that were lining up with the columns that had the pivots. And then the other variables, the ones that don't have any pivots on them, those are called free. Those are the free variables. So I'll add that to this as well. The free variables, and in our example, let's see, in the example, the free variables, the ones that don't have pivots, I see a V and a Y, right? So in our example, that would be the V and the Y. These correspond to the non-pivots. Those are the ones that don't have pivots. So every variable is either a leading variable or a free variable, depending on whether it corresponds to a pivot or not. Okay. And now in this setup, I have two free variables, which are V and Y. Now I talked about solving the system by back substitution, which of course sort of means you start at the bottom and you work your way back up. Yeah, that's kind of the general approach. But then even just, let's look at this bottom equation. I don't even really know how to start that. I mean, I've got two variables appearing in this last equation here, right? One of them is a leading variable, one of them is a free variable. But I think you guys would all agree, if I gave you a value for X, then you could figure out what the corresponding Y is. Or if I gave you a value of Y, you could go back and figure out what the corresponding X is. So one of those two variables should be freely chosen to be whatever number you want. And then the other one will be forced by the equation to make the equation true. We are going to adopt the convention here, guys, that the free variables are absolutely what the name says. They are free. They can be anything we want. So what we're going to do, we're going to go back now and solve this system. So I'll just go ahead and, I've already written solution once. Now I'm really doing the solution. Everything else was just kind of setting it up. For this solution, I'm going to let Y be equal to, I'm going to use an R to denote it as a free variable. Now, I always get this question, why are you bringing in an R here? You don't have to. You can just leave it as a Y if you want. However, on every different problem that we do, there will be different letters that are being used. And I like to kind of always reserve, you're going to see me do this all semester, I'm going to be using R, S, and T for free variables regularly. So that anytime you see an R show up on the board or a T show up on the board, something like that, you're going to be thinking, ah, that must be a free variable. When I say free, I mean exactly what the word says. It can be any number you want, right? I can choose Y, which I'm now going to relabel as R, to be any number I want. I can choose it to be 100. I can choose it to be negative pi. I can choose it to be 5 billion. It doesn't matter. As long as I have a value for Y, then I will have X determined from that last equation. Namely, what is X? X is 5 minus 3Y, according to the bottom equation. But I am going to rewrite that as 5 minus 3R. I'm going to try to write every one of my 5 variables in terms of the free ones. So my free variables, so far I have one free variable, which is R. So you're going to notice that I'm going to try to write X in terms of R. And I'm going to do the same thing with W. So then now I go back substituting into the previous line. Let's look at what W is. W, according to the middle equation, right? What is W? Well, it's going to be negative 3 plus X. So just solve for W on that very first equation. On that middle equation, sorry. On the middle equation, we can solve for W, negative 3 plus X. But again, I don't really want to call it X. I want to get it in terms of the free variable. So I'm going to replace the X with 5 minus 3R. So I had negative 3 plus X, but I'm replacing what X was. And I'm actually going to clean this up just a little bit. Negative 3 plus 5 is just 2. So this becomes 2 minus 3R. And that's the W value. So far, I'm not done yet. I'm currently doing this back substitution process. I have a free variable for Y. I have back substituted for both X and W in terms of that same free variable, which by the way is R. And now I'm pretty much done with W, X, and Y. But I still have the U and the V. V was one of my free variables, right? So I'm going to establish another letter for that. I'm going to let V be, I'm going to use T. I actually don't like to use S very well because S's look like 5s when you write them down on paper. So it's just a little easier to skip over the S and use a T. So V is also free. So R and T, those are my favorite letters for free variables, and I'll be using them all semester long. But once I've done that, then I can write down what U is. So here's U. This is the one that's going to take a little bit of writing. If you solve for U right now, let's see, it's 3/2 of V minus 1/2 of W. Guys, I'm actually subtracting. I'm moving everything to the other side of the equal sign of the first equation so that I can solve for U. So you'll notice that the signs are kind of going backwards here. So then we have a plus 1/2 X and a minus 1/2 Y. All right, that's good enough, but then see, I've got to write it in terms of the free variables. So in this case, the V was replaced with T, right? And then minus 1/2 W. What was W? W was the quantity of 2 minus 3R. And then plus 1/2 of X. X was the quantity 5 minus 3R. And then minus 1/2 of Y, but Y was the same as R. So I write everything in terms of those free variables, like so. Okay, and that should be simplified. Let's actually simplify this, guys. I hope I can write down here. If you need to stand up in the back, feel free to do that. Sorry, I got running just a little short on space, but I want to squeeze this in. This is 3/2 of T. You'll see that one. But then I have a bunch of terms with R's in them. If you clean up all of those R's, it actually will come out to just negative 1/2 of R. Sorry, negative 1/2 of R right there. Okay, I'll let you check the little arithmetic on that. Minus a 1/2 of R. And then there's actually a constant term as well. You see the -1 right here, followed by a plus 5/2 right here. Now that's a net total of a plus 3/2. So you should have a plus 3/2 on that as well. Okay, so there you have it, my friends. That is U, V, W, X, and Y. Is everybody understanding that? That's the process there. That, however, is not a great way to write the answer. So this is all of the heavy calculation work, and we've got certainly everything is pretty much solved, but we should write our answer in a better set notation, which I'm going to describe right here. So what I'm going to do, guys, is I'm going to write my solution set. And I'm going to use these big braces. So we're just going to kind of adopt a little notation for this. Inside of these braces, I have 5 unknowns. So I need to make sort of a 5 tuple, 5 slots here. And I need to put these unknowns in the correct order. U comes first, then V, then W, then X, and then Y. So what is U? That's the one on the bottom of the board there. 3/2 of T minus 1/2 of R plus 3/2. And then I'm going to put a comma. And then the next variable that I need to write down is V. So I can look back over there. What was V? Oh, V was just T. So I put T and then comma. All right, then my next unknown is W. W is 2 minus 3R, comma. And then the next one is X. X was 5 minus 3R, comma. And then the last slot, the last unknown is just Y, which is just R. So then I'll close my parentheses on that. And then I'm going to do this. I'm not quite done yet. I'm going to put a little colon here. Little colon here. This colon is just, this is just math notation. It just means such that. And then we'll have R, comma, T, elements of the real numbers. So this little sort of scripty E thing is just belongs to. So it belongs to the real numbers. This is a great way to write out the solutions to this system. It's a great way to do it. Okay. Questions on any of that? How many solutions does this system have? Say it again. Infinitely many. There are infinitely many solutions here, right? Infinitely many solutions. Why is that?
It's for all real numbers.
We got any number of choices for R and T, right? Everybody in this room could pick their favorite R and their favorite T, plug them into those 5 slots, and come up with a valid answer, right? So everybody on the planet could make up their solution here, right? So there are infinitely many solutions since we have free variables. That's the reason. That's the reason that there are infinitely many solutions. Is it Edgar? Yeah, what's up? I don't think so. I appreciate, you must know exactly what I'm going to do next. I was going to remind you of an example that we did last Thursday. It's a great question. Absolutely great question. Do you remember this example? We had 2x minus y plus z equals 6. And then we had 4y minus z equals 8. And then we had z equals 4. This was the one that was already kind of in that quote unquote triangular form. And you may remember we just solved it directly by back substitution. And we came up with the solution. I actually did write this down in the lecture last week. 11 over 2, comma 3, comma 4. Right now, this one, we have only one solution. Because you had, no, basically it's because there's no free variables. Yeah. I mean, if you were to write down the A sharp here, I guess I'll just do this. You know, you could write down this this A sharp matrix. This is a short little thing to write down. Your A sharp matrix looks like that. And if I start circling where my pivots are, technically they're not pivots yet, but we could make them into pivots very easily. So these are the positions where the pivots will be. And you can see that the unknowns, none of them are free. None of them are free. There's no free variables, and therefore we do not get infinitely many solutions. Right? So you see the difference? The real reason that you would ever have infinitely many solutions, right here, is because we have free variables in the row echelon form. Free variables just means that basically there's some columns without pivots. In this case, the B column and the Y column did not have pivots. See? Okay, so it's possible for a linear system to have infinitely many solutions if there's free variables. It's also possible for your system to have just one solution, which is what this example shows us. I can think of at least one other possible outcome. Can anybody think of another possible outcome for how many solutions your system might have? It could be one. It could be infinitely many. Any other answer that you kind of know would be correct? Say it again. 0. Yeah, 0, right? What if I had x plus y equals 2 and x plus y equals 3? I pretty much know that that has no solutions. But you know what I would like to do? So this has 0 solutions. It's just kind of obvious. I would like to just play the game of what the Gaussian elimination would tell me. Like, let's just want to see how this would play out. Okay, so if I actually did this one, we would write down our A sharp. It's really short, right? It's just, this is the matrix right here. 1, 1, 2 and 1, 1, 3. And, you know, I've already got my pivot in the first row, no problem. And then I just have to do one ERO here. I need to get a 0 underneath this first pivot. I'm just trying to play dumb for a minute and just say, oh, what happens if we try to do the Gaussian elimination on something that doesn't have any solutions, right? So if I just, what am I going to do here? I'm going to add the first row onto the second row with a multiple of what multiple? To get this to be a 0, what do I need to multiply the first row by to add to the second? -1, right? -1, exactly. So -1 of the first row added to the second row. And if I do that, this is what I'm going to end up with. See what's going on? Guys, we could now take this, and just like I did over here, remember once I got it into row echelon form, I went back and rewrote the system again. Well, I could do that here too. I could say, well, now let's write down what the system is. The first row is actually the same as it was originally, but the second row is, what's the second row? 0 times x plus 0 times y equals 1. And now you see very bluntly in your face that this is crazy, right? This cannot work. I don't care how hard you try to find x and y, nothing is going to work here, right? So this system has no solutions. No solutions. Okay, so it turns out, my friends, that these 3 examples that I've just shown you illustrate every possible scenario. Your linear systems, guys, in this class, well, in any class on linear algebra, they will either have no solutions or exactly one solution, or if there are free variables, infinitely many solutions. That's it, right? So there are three possible outcomes to Gaussian elimination. I'd like to, this is a good place to take some notes to put it into a summary. So we kind of summarize what we've observed in these last few examples, right? So the first one is, the first possible outcome is that we would have infinitely many solutions. That was what we saw in that first example. This would happen if this happens when we have free variables. Okay, maybe just so you have a little visual in your notes that goes with this, I could kind of draw it out. There's like a pivot there maybe, and then some stuff. Then we maybe we have a bunch of zeros and then some stuff, right? But see, you've got some columns here that are unpivoted. those unpivoted columns, right, they correspond to free variables. So if we have free variables, then of course we will get infinitely many solutions. That's what happened over here, right? Okay, that's one possibility. The second outcome is that we could get exactly one solution. Okay, we could get exactly one solution. This one happens when we have no free variables. Right, so infinitely many solutions, that would be if there are some free variables, at least one. One solution would be there's no free variables at all. So how would that look in a matrix if I had like some row echelon form? Well, now what would have to happen is, guys, you would have pivots filling up every single column. It's exactly what we have in this example here. There's no columns without pivots, right? So in that case, you can still solve it by back substitution, but you're never going to be introducing any free variables. So you just get one solution. So it's just what's shown on that example there, right? And then the third outcome, right, the last case is we get no solutions. By the way, does anybody remember what the word is for that? If there's a system that has no solutions, what did we call that system? Inconsistent, right? So this is the inconsistent case where there's no solutions, yeah? And this would happen, when does this happen? This happens when a pivot is in the far right column. If we get a pivot that has drifted all the way to the far right column, then that's going to be inconsistent. So now what we're saying is that you have a pivot like way over here somehow. Because if the pivot is way over there, then to its left must have been nothing but zeros. And now you've got kind of a nonsense equation here, right? Just like what we wrote down here, 0 times every variable adds up to 1, right? Just doesn't make sense. You cannot solve that. So that's it. You cannot have a system with 17 solutions. You cannot have a system with 1,000 solutions. Systems of equations will always, linear systems of equations will always have either no solutions at all, exactly one solution, or infinitely many solutions. Is everybody with me? Are there any questions so far, guys? Fantastic. Okay. I want to do one more, before I move on to the next section, I want to do one more example on this because I put questions like this on some of my exams in the past, and sometimes people just maybe just don't quite know what to do with it. So I'm going to just show you one more example here, and then I'm going to be feeling pretty good about this section. Okay, so one more example. This example is going to help us review all of this in kind of one example. So I'll show you what I'm talking about. Let's do this example. Let's determine the values of K such that, let's determine the values of K such that the system below has, and I'm just going to put down the three cases, infinitely many solutions for part A, part B will say one solution, and then part C will say 0 solutions. Okay, so I'd just like to know for what values of K does my system have each of the three possible outcomes. Okay, so what's my system here? I've got to give you a system. So here's the first equation. X plus 2y minus z is equal to 3. The second one is 2x plus 5y plus z is equal to 7. And then the third one is where the k shows up. So it's x plus y. And then here's where the k shows up. It's going to be minus k squared times c is equal to negative k. Is equal to negative k. So there is a k in this system, but k is not one of the unknowns, right? The unknowns are just x, y, and z. The k is just some parameter that is going to have some value. It's going to be some specific value. Okay, so this is my system. So far, so good. But what I have to do is, of course, to solve this problem, I'm going to put the whole thing into a augmented matrix. So let's write down the augmented matrix for this. A sharp, right? So A sharp, I'll start right here with this. A sharp is going to be, the first row is 1, 2, -1, augmented with 3. And the second row is a 2, a 5, a 1, augmented with 7. And then the third row is 1 and 1 and negative k squared and negative k, augmented with negative k. So there's the A sharp. All right. For the moment, I don't want to flinch because of the k that's in there. I'm just going to play the game the same way I always do. Just kind of do my EROs. Okay, so don't worry about the k. We don't know what a k is right now, but I'm just going to go through the motions again, right? So I've got my pivot right here in the upper left corner. That's great. And I need to get zeros below it, right? The trick here, right, the most important thing, right, is to get zeros below that first pivot. So here's my first row. I have a 1, a 2, a -1, augmented with a 3. All right, and then let's get the ERO. This is good practice on the EROs again, right? To get a 0 here, I got to use the first row to create that. What's the ERO using my notation? I guess I've erased it now, but do you remember the notations? A12 of -2, right? So I take -2 times the first row. I'm going to add that to the second row. So let's go all the way across the first row. I'm mentally multiplying through by -2 and adding to the second row. I'll get 0, 1, 3, and 1. And I'll circle that pivot right there. Trying not to go too fast. Just depends on how much sleep you got last night. It's how fast you can kind of do that in your head. I also want to get a 0 down here in the bottom row at the beginning. So how do I want to use this pivot. How do I use that pivot to turn this 1 into a 0?
A13.
A13 of -1, right? Negative. So that takes the negative of the first row and adds it to the last row. So I'll get 0 and then -1, and then I'll get a 1 minus k squared, and then I'll get negative k minus 3. Right? So I'm taking the negative of the top row and adding it to the bottom row. And I now have a nice pivot in the second row. It's already a 1, so that's good. Let's do another ERO. Does anybody want to suggest what ERO I'm going to do now?
A23.
A23 of, I like it. So
1.
just 1. I'm just going to add the second row to the third row to turn that into a 0. You got it. So A23 of 1. Let's write it down. The first row stays the same. No change there. The second row also just stays the same. No change there. The third row, when I add the second row to the third row, I get a 0, and then a 4 minus k squared. And then I add 1 to negative k minus 3. It becomes negative k minus 2. Okay. Everybody with me? That's about as far as we can go for the moment with EROs. And I'm going to start analyzing what we have there. Before I totally erase this board, remember this example. Because I had pivots in every column over here, we had one solution, right? So I'm wondering over here, I've got pivot, another pivot. Is this going to be a pivot? 4 minus k squared, would that be a pivot? I claim it depends on what k is, right? If k is equal to 2, then that's not a pivot, it's a 0, right? But if k is any other number that would make this thing not 0, then it's basically a pivot, because then you can always take a reciprocal and turn it into a 1, right? So I claim that if, let's just write this down, if 4 minus k squared is not 0, and let's just say i.e. k does not equal plus or minus 2, in that situation, then we get one solution. We're in this middle case, right, where you have no free variables, the pivots just go straight down the diagonal on the left side of that bar. That's almost every possible value of k. The only thing it's leaving out is k equals 2 or negative 2. Well, we could look at those separately. If k equals 2, let's just think about it. If k is equal to 2, let's read the bottom row here. If k is equal to 2, what do I have? I have 0, 0, 0, and negative 4. Right, if k equals 2, I'd have 0, 0, 0, and then on the right side, I'd have a negative 4. Which case is that? No solutions, right? No solutions. If I have 0, 0, 0, and negative 4, I'm putting a pivot in the far right column in that case, right? So in this case, 0 solutions. Right. And then if k equals negative 2, if k equals negative 2, then what's the bottom row looking like? Then if k is equal to negative 2, then I have a 0, a 0, a 0, and a 0 again, right? The bottom row is all zeros. In that case, actually would have a free variable in this third column because it would be, no pivot there. But you wouldn't have a pivot in the far right column. That would be infinitely many solutions in that case. So depending on what k is, you could get all three of these outcomes potentially. So I just want you to think about it. Basically, k is just some parameter. We don't know what it is, but it's some fixed number. Depending on what it is, depending on what that value is, that dictates which of our three outcomes we're looking at for that problem. Yeah, that's exactly how this works. Does this make a little bit of sense?
I'm just confused. How is it like infinite solutions when it's like 0?
In this last case? Yeah, so what would happen is, the first two rows would be the same as what I have over there already, right? So it's going to look like that. The second row, it's just going to be like this, right? But then in the case when k equals negative 2, if you plug it into the bottom row, look, you're getting all zeros everywhere across that whole row.
Shouldn't that row be
Basically, this row is gone. You want to think of it that way? In fact, you'll see me start to do that later in the semester. I'll just cross off the row. It doesn't even matter. The row is completely worthless. I think I said that last week. If you have a row of zeros in your matrix, it tells you nothing, right? This row tells you that 0 times x plus 0 times y plus 0 times z is equal to 0, which tells you nothing about what x, y, or z are, right? Because it's just always going to be true. So it's kind of worthless information, but in the context of looking at the columns and the pivots, which is really what you want to be doing, this z variable here would be considered free right here. The z would be free in this third case. There's no pivot there. And then you could use back substitution to write x and y in terms of that free variable. Go ahead.
In this case, k is just a constant.
It is.
Okay.
Yeah, it's just some number that's not changing. Other questions so far? I want to make a quick observation here with you guys for a quick second. Maybe I'll just call this a note. I want to go back. I want to go back to that very first system that we started with today. Let me see if I can write it. I'm going to write this down one more time. I swear it's the last time I'm going to do it. This is the system that we started with, 2u minus 3v plus w minus x plus y equals 0. And then the second equation was 4u minus 6v plus plus 2w minus 3x minus y equals -5. And then the third one was -2u plus 3v minus 2w plus 2x minus y equals 3. This is where we started today with. I mentioned, of course, that this thing has infinitely many solutions and we solved it out. I want to make a completely different remark right now. Okay, so obviously the way we solved this was we wrote down the A-sharp matrix. Okay, I would like to propose a different way that we could maybe solve the system and get your opinions about it. Okay, you maybe didn't think of it this way yet, but I actually claim, I'm going to rewrite this. I actually claim that we can rewrite this in a slightly different way. I, of course, have my right-hand side values. I'm actually going to put those into a vector. I'm going to kind of make them into a column vector here. But you know, when I look at the left-hand side of this system, well, what it looks like to me is actually each one of these equations, believe it or not, I can recognize it as if it was a dot product. 2 times u plus -3 times v plus 1 times w plus -1 times x plus 1 times y. That's like dotting two things together. And in fact, I'm going to try to convince you of this, right? I'm going to put my u, v, w, x, and y like a column right there. And where did we see dot products coming up so far this semester? In the matrices. In which operation with matrices has dot products that you have to do? The multiplication, right? Yeah, exactly. Matrix multiplication. Guys, if you take these numbers, 2, -3, 1, -1, and 1, and you multiply it by that column, you literally get the left side of the first equation. Okay. And then if I play the same game on the second row, I would just have 4, -6, 2, -3, -1. And then if I do the same thing with the third row, I would have -2 and 3 and -2 and 2 and -1. So instead of the augmented matrix, what I actually have on the left here is just A itself, not A-sharp, but just A without the right-hand side vector. Let's just look at this, and I want to see what you guys think about maybe another way to solve the system. By the way, it's going to turn out to crash and burn. It's not going to work, but I'm just trying to be, I'm just trying to propose something here and see what you guys think. Guys, would you agree? I could view that as the big matrix A. I'm just going to rewrite this times this column of unknowns here. Usually with that, I'm just going to draw it as a vector with an X on it. So this column, U, V, W, X, Y, those are the unknowns. And I would like to set that equal to what I'm going to usually denote as a B vector. That's just the numbers on the right-hand side of my system. What I'm trying to say here, I don't know how well I'm saying it, but what I'm trying to say is that you can always write a linear system of equations. Instead of the A-sharp that we've been using to do the EROs with, we can instead write our linear system as a matrix multiplication. Right, with the unknowns being laid out as a column vector X in the left-hand side. Okay. And this totally makes sense. You have, you know, whatever it is, this is going to be an M by N matrix normally. The number of unknowns is always the same as the number of columns that you have in the matrix. So that's going to be represented as an N by 1 column. And then, of course, on the right-hand side, you end up with this column that is M by 1, which are just the values on the right-hand sides of all of your M equations. So this matrix multiplication, the sizes of these things, they are compatible, right, with each other. Yeah. So far, so good. So my idea for solving for the unknowns here is that I would like to just move the A to the other side of the equation. I want to isolate the X, the unknown is the X here. So, I mean, if you showed this to somebody in 8th grade or something and said solve for X, right? They probably would be thinking about getting the 10 out of the way, get the X by itself. And of course we could all do that. So can we do that here? I already gave it away. I said this is going to crash and burn. Yeah, we cannot do this. Remember we talked about all the operations on matrices? Oh my gosh, what was it? Transpose, derivatives, integrals, limits, addition, subtraction, multiplication, scalar multiplication. All of that was fine, but we never said a word about dividing by a matrix, right? Which is technically what you'd have to do right now, right? We cannot divide by a matrix here. So we cannot solve for X by dividing by A. I proposed to our publisher, should we at least say something like that in the book? And they're like, don't even mention it. Don't even give anybody the wrong idea. We cannot do that. Anyway, I'm going against my publisher and mentioning it. But no, we cannot divide by a matrix. The question is there something that we could do that would be sort of equivalent to that? And it turns out there is. Except that it doesn't always work. Of course, it also doesn't always work with numbers either, right? If I ask you to solve for X here, right, of course, you're not going to divide by 0 to solve for X. That's an illegal operation. So dividing by things is, even with numbers, not always legal. It turns out with matrices, it's illegal much more often, right? But there are some situations when we can do this. So there is a, what am I going to try to say here? There is a way to mimic this in some cases using something that I'm going to talk about now, and it's actually the start of the next section here, and I'm just going to get this started. 2.6. We can mimic this process in some cases using something that we're going to talk about next called the inverse of a matrix. Okay, so we're not going to divide by a matrix, like literally. That's going to be against our rules in general. But we can do something in some cases. It does say in some cases, not always. In some cases, we can do this. So let me just set this up, then we're going to take a little 10-minute break here in a minute, but I just want to get the definition down. So we'll be in a good place to sort of continue this conversation. Well, the very first thing is that if you want to do this mimicking thing, your matrix A, it turns out for this section, it has to be a square matrix, n by n. So we're already out of luck here. This matrix is what, 3 by 5, right? It's not even a square matrix. So we wouldn't have been able to even get to first base with this previous example. You've got to have a square matrix here. But if there is, so here's a little bit that we can add now. If there is a matrix B, which is also the same size. So if the matrix B is n by n, such that, okay, such that the following is true. Let's see how well people remember from last week. You guys remember our good friend, the identity matrix, this I sub n matrix? If you need a quick recall, I'll just scribble over here for a second. This is the matrix that has ones kind of on the main diagonal and zeros everywhere else. That 7-minute video that you guys watched, it has a little talk about that in it. That's your identity matrix. Remember, that's the matrix that sort of stars in the role of the number 1. It plays the role of 1. It's like if I multiply that matrix by anything else, it just leaves it alone. The same way that multiplying by 1 leaves everything alone. So in other words, guys, if this equation is true, then the matrices A and B, they're kind of like reciprocals of each other. 7 times 1/7 would be equal to 1, right? So it's kind of like that. And it turns out that we don't actually have to check this, but the multiplication in this case is actually going to work in both orders. Now, normally, we talked about this a lot before. Normally, the order of the matrices makes a difference, and we should not assume they will be equal. But when you multiply the two together and get the identity matrix, turns out it's going to work in both directions automatically. We don't actually have to check that. If there is such an equation, then A is what is called invertible, and B is an inverse of A. In this case, B is an inverse of A. So it's kind of like a reciprocal of A. You can use it to cancel out the matrix A. If I take A and I multiply it by B, I get 1. It's like canceling it out. And that's effectively like dividing it out. Okay. So if I wanted to isolate this X, for example, what if I multiplied on the left by B here? Well, BA would get replaced by I, but I is like 1. 1 can be ignored, right? You just get X by itself in that case. I'm going to write that down in the notes. Anyway, so this is the idea of an invertible matrix and how the matrices A and B are related. They are inverses of each other, right? Okay. So let's, I have a lot I want to say about this. This is a big section. I just barely started it. But let's take 10 minutes to get some fresh air if you want. I think the sun might just be going down. If you go down the end of the hall, there's a balcony out there with some fresh air if you want, or grab some water, or stretch your legs. If you've got questions on tonight's homework, during the break would be a great time to throw some problem numbers on the board there on the side. And then in 10 minutes, at 5:15, we'll start back up one more time.
You said tonight, be okay to come out this hours?
Should be great, yeah. Oh, anytime is
I have,
okay.
like, a lab that's like starts at 7, so I think get out around like 8:39.
Beautiful. At 9 is when, at 9 o'clock is when I take my little dinner break. So just so, but I'll be coming back. You can study out there as much time as you need. Yeah,
too,
exactly.
so.
It's down in the basement of the
Okay,
building.
yeah.
So it's MH33. Yeah, that's it. Okay, sure.
Lambda is.
When we come back.
It's like K. It's Lambda. It covers mainly like when you're working. Oh, that one. Remember when we covered the variables? I was looking for the time. I'm already ahead of some minutes. What is your name?
Okay, I just was trying to figure out if I was supposed to be in the song.
The day of his
Maybe that's what.
But you're.
You're in. You got it before. Okay, good. Glad that worked out. It's like. Whew. It was. I was like, I couldn't look at it. I thought it's not gonna be a problem. It's in this room. Like some rooms, I can just like throw extra people. It's not all in this one. They're very strict about because. Yeah, they only use a certain number of tables. not gonna be much I can do. Luckily, there was somebody. That helped. Anyway, it's nice to see you. Yeah.
Ah, there we go. I get that. That's the one where. Yeah, I think we can say that's top three goes at it. It's interesting where the matrices. Top three.
Did anybody happen to bring the book with them tonight? Do they have a copy of the book with them? I just need to look up, I have my book, but I'm using it as a sort of balancing thing for my camera. I just need to look up what those two products are. I think I remember what 32 was, but you have it somewhere here.
Yeah.
Yeah, so you just need to go to 2.1 and look up number 7. Okay, can I bring you up here for a second? So number 7, let me just make sure I get those numbers down. There's a lot to write down. A12 is -1. A13 is 2. And A23 is 3. And then they give you AJI, -AIJ. And that's gonna be with I between 1 and 3 and J between 1 and 3. Not that one, and then I'm gonna slide over here and go to 32. What they wanted to ask me about. I think I know 32, but I just want to double check it.
Oh, this one's the proof one.
Yeah.
I think, okay.
Yeah, so this is the saying, show. That if A, n by n, it says, symmetric. And upper triangular. Huh? Then A is diagonal. Okay, yeah, that's what I thought. Thank you so much. What was your name again? Omar. Omar, thank you so much.
I still have a question. I was looking at that one and when we and okay, proof of it.
Probably not. This is saying that you're basically saying that every single entry is zero. My non-equal J implies, not since, but implies that AIJ is. That was meaning the non-zero could be broadly one. So that part is right. Just up here you have AIJ. I think you should just say, when I does not. J. If you say that, then I think it's.
Yeah, do you buy like other fish?
Let's start with. Yes. When we get to chapter 4, we're not that far yet.
I did take note of like this. Some of the, you know. The trials. That's safe for that one. That one was just pure muscle. So it's like, okay, cool. So put this together. I thought.
But then it's also like.
Oh. Give me a second. I'll tell you. What format? What is? Yeah, so why not? I've never seen that. That's true. You put it wider and then you get so big. Yeah, it's so it's not too far out. Okay, so keep your eyes peeled. Your emails for the next 7 hours. I'll see what. Okay.
All right, guys, I think I'm gonna go ahead and pick things back up here again. Before we do anything else, though, I would like to just check off the names here on my roster. I know a few of you, but it's gonna take a while. And I forgot to mention, did y'all see in my syllabus about the thing about the 5-minute introduction at my office? I was gone for the first 2 weeks, so a lot of people probably waiting until I come back, but you're welcome to do that anytime. If you stop by and introduce yourself, this week is fine. Even I'll probably extend it and let you do it next week if you don't get it done this week. If you do that, I am going to do the following. It's something new I tried last semester and the students loved it, which is I'm going to basically make you eligible to do extra credit for each exam. The extra credit would be a couple of things. One is believe it or not, in my SOQs, students have been telling me that they wish we could have quizzes in class. I don't know, that must be some students that like quizzes. Anyway, they said it would be good, it would be helpful, but I just don't have a lot of class time for quizzes, so I don't like to do quizzes in class. So I thought, well, the compromise is I can let you do a quiz so you can get the feedback on it, but do it as a take home that's like some extra credit outside of class. So I will be doing that for each exam, roughly a week before the exam. I'm gonna make a little one-page quiz thing. It won't be long, but just like a couple things for you to practice on. And as long as you've done the intro and said hello to me at least once, sometime either in Zoom or in person, you will be eligible to get those quiz points. In addition, there will probably also, along with that, be a video to watch. Remember how you took notes on those videos and submitted those into Canvas? I am probably going to have some videos like that. They won't be optional anyway, so everybody's gonna have to do it. And so I want you to get extra credit for that. So to help you get extra credit for that, I just need you to stop by and do that quick little introduction. This week would be great. Next week is also fine. Just less than 5 minutes, just stop by my office. I learn names much better when I see one or two people at a time rather than trying to learn everybody right now. But I still am gonna go over this roster just because I wanna see how I'm doing also with attendance and enrollment issues, because I talked about the enrollment earlier too. So just holler out if you're here so I can kind of take some notes on this. Jesus, you're here. I saw you. And Anthony is here. Omar, got you. Omar, thank you. Elijah, thank you. Bon, got it. And James is here. Marissa, thanks, Marissa. Okay, great. And Zach is here. Eric Gonzalez, thanks, Eric. Gotcha. Nathan, I just met you. Nathan Hawk, met you earlier today. Thank you. Alex is here. There you are. Thank you. Joe Jimenez, got it. Thank you. All right. And then David Lamb. Is David here? No, David. Okay. How about Andy Lee or Lee? Lee. Thank you. Got it. Nathaniel. Thanks, Nathaniel. And then Angel or Angel, is it Angel? Okay, got it, thank you. And Joanna, thanks Joanna. Daniel Perez, thank you Daniel. And then Fook.
How you doing?
Am I pronouncing your name correctly?
Perfectly.
Perfectly, okay, excellent. I'm from Nebraska, I have no accent and I can't pronounce.
Yeah, a lot of professor, especially in the engineering department, they like couldn't pronounce it.
Couldn't pronounce it, okay, all right.
Got it first try.
Perfect. Okay. Antonio. Thank you. Gotcha. And then Mohammed. Mohammed. What's your last name? Sophia. Yes, I got you here. Yeah. Thank you so much. Perfect. Stephen. Thank you, Stephen. Aaron Rivera. I guess I haven't quite met you yet, but I did now. Thank you, Aaron. Edgar, I know I've met you. There you are. And Angelica, met you. Brighton. Am I saying that right? Okay, sweet. Tiffany. Thank you, Tiffany. Kevin. Kevin's here. Great. Vinny, I met you earlier. Andy Vu. Thanks, Andy. And who else do I have here? Milton is here and Gwen is here. Okay, is there anybody here whose name I did not call? I know I did not call yours, Brian, and you are Stefan? Okay, let me just really quick, I just want to double check that I'm not doing anything wrong here. Is there and somebody else had their hand up. What is your name?
Eliud.
You are, how do you spell that?
Elihu.
Okay, so I don't have you on my waiting list at all. Okay, and I thought I had you, but I don't seem to have you enrolled. Stefan. What was your last name again?
Straussman.
Okay, and then Ryan, I know your situation. 1 second. I have an idea here. I just have to go over to this other. Sorry, guys. I will figure this out. Let's do a quick chat after class. Yeah, let's do it that way. I can't quite find your name in my system somewhere, but I thought I saw it at some point. Not sure. Okay, guys, a couple people put a couple of problems on the sideboard over here. This is for tonight's homework. So I'm just gonna take 5 minutes maybe and help you with these two problems, and then we'll go back to our notes again. Okay, so we'll try to finish up this way. Number 7, these are both from the first section, 2.1. Number 7, they give you some values here, and then they ask you to like write out what the matrix is. You can see that the size of the matrix on this problem is going to be 3 by 3, and this is because the I and the J, I think I might have neglected to kind of explain this notation. If I see like A sub ij, that's just talking about the entry that's in the row I and column J, right? So like if A12 is -1, that's just the number that's in row 1, column 2. Okay, and then A13 was equal to 2, all right, that's row 1, column 3. And then the A23 is referring to the entry in row 2 and column 3, and they gave us that number as 3. So they gave you the values that I've already filled in there. And the question is like, well, what's the whole rest of the matrix supposed to be? And the thing that you need to do to find out these other 6 numbers is to look at this thing at the bottom here. Is it tells you kind of how to do the AJI versus the AIJ. There's just a sign change. So if I wanted to know like what is A31, which would be this number right here, right? Well, that's just, they told you that you need to take the negative of A13. So whatever A13 is, you just put a minus on it. So that was a 2, but this one is actually going to be a -2. Just a sign change, right? Just a sign change. Let's just do one more of these, A32, right? Just go with the flow of what they told you, right? They said, well, that's the same as negative of A23, but they gave you A23 is equal to 3. So then A32 is -3. Okay. Making sense? Now, what about like something like A22? Because that would be the middle entry, right? Row 2, column 2 in the middle. Well, they didn't tell you specifically what that is, but again, using this last formula, A22 is equal to negative A22. What's the only number that could be then? 0, right? Right. The only number that equals its own negative is literally 0. So A22 is 0. And actually, by the same token, A11 and A33, they have to be 0 as well, right? So that's the deal. And then A21 is just the negative of A12, so that's going to be a 1. What kind of a matrix is this? There's a word. I heard it. Skew symmetric. Yes, it's skew symmetric. So this is a matrix. You might remember from my little video there that the condition is that the transpose of the matrix is equal to the negative of the original matrix. Right? That's skew symmetric. That's a skew symmetric matrix. Okay. Anyway, so that's how you do number 7. And you don't have to show a lot of work. You can just write down the answer. That's pretty much good to go. 32, I usually get asked this question because it's kind of more of a proof. You have to actually write an explanation here rather than any kind of calculations. This is supposed to be something that would work for an n by n size. So one thing you want to avoid here is don't get caught in the trap of like showing me an example of a 2 by 2 or a 3 by 3. You can't draw specific matrices for this. Instead, what I'm going to be doing here, guys, is writing in words an explanation for this, right? That's basically what I'm going to do. So let's just write a paragraph to explain it. And it's a paragraph that would work even if my matrix was 1000 by 1000, right? It's something that would work for any size of a square matrix. Okay, so since A is upper triangular, and of course I'm relying on you guys having watched my little 7-minute video for this. If you remember upper triangular, I'll just scribble here if you don't mind for a second. That just means that everything down here is all zeros. You can have any numbers you want anywhere else. But below this so-called main diagonal, the entries must be 0, right? So let's just write that down. Since A is upper triangular, all entries below, all entries below the main diagonal are 0. That's just a starting. So it's upper triangular. So everything in sort of the southwest corner of the matrix, right, the below the main diagonal, those entries are all 0. But we know more than just that. Not only is this matrix upper triangular, it's also symmetric. And because it's symmetric, remember, that just means that if you flip the matrix along that main diagonal line, right, do a sort of a mirror image, everything above this main diagonal has to look the same as what's below the main diagonal. So I'm just going to add that, another sentence here. Since A is symmetric, this implies, you're welcome to just copy my solution exactly if you want to. And let me know if my grader takes off points. No, I'm just kidding. Anyway, if A is symmetric, this implies all entries above the main diagonal. So we just need a couple sentences. All entries above the main diagonal are also 0. Yeah. So everything below the main diagonal and above the main diagonal is 0. We haven't said anything about what's going on directly on the main diagonal, but actually that doesn't matter. To prove that A is a diagonal matrix, you might remember from my video, a diagonal matrix is just one where everything off of the main diagonal is 0. And we've already said that that's the case, right? So this means A is a diagonal matrix. That's it. So just a quick little 3 or 4 sentences. It's about all it takes. But it needs to be kind of done in this way. I sometimes will see people, they'll write out a matrix. They'll say, well, I'm gonna do 1, 2, 3. There's an upper triangular matrix, right? They'll start getting specific, and it's almost too specific. It's like I wouldn't be convinced by that. It's like if I make the claim that all Saturdays are sunny, and we go outside this Saturday and it is sunny. You're probably not going to be convinced that my statement was true. I might have gotten lucky with that one particular example. Same thing here. Might be some example that works, but I need sort of a more general explanation that could be irrefutable in any case. So something like that would work great. Okay. So I hope that's okay. If there's anything else that comes up between now and midnight on the homework, I will have all those office hours later on tonight, and you certainly can follow up with me. The assignment shouldn't be too bad. This one, I hope, unlike the one for Friday where you're going to really have to be focused on those EROs, this one is more just kind of casually work out some sample problems. Okay, well, we've got about 20 minutes here. I want to come back to the conversation we were having before our break here tonight, guys. I was trying to float this idea of mimicking the idea of dividing by a matrix by using an inverse instead. And I want to pursue that a little bit further. Okay, I'm going to try to pursue that a little bit further. I'm going to come back over here to do it, though. And I'm going to ask a question here. Just because I'm a mathematician, and so I get curious about things really easily. My question I'm going to ask here, guys, is can a matrix have 2 inverses? Let's just remember, I tried to keep this definition up here for a reason, so we can be looking at it. An inverse is just a matrix where, if you multiply A by its inverse, it cancels out to the identity matrix. The question here is, well, could there be 2 different matrices that both serve as inverses for A, right? So the theorem is actually, the answer to this question is actually no. There cannot be two inverses for a matrix. So if a matrix is invertible, it will have a unique inverse. Let's actually state that as a theorem. So a theorem here, if A, which is n by n, has an inverse, that inverse is unique. There is only one of them. There is only one inverse matrix here. I'm just going to close this door a little bit. Too busy for me. Yeah, so you know what? Mathematicians like to prove something like this. You are going to see me giving you a little bit of this, a taste of this in this class, a slightly more theoretical side to the material, and just a little exposure to what theoretical math is about, and that would be doing proofs to justify these results. Anybody have an idea how you prove that something is actually unique, that there could only be one correct thing? Yes, maybe there, imagine for a moment hypothetically that there were two inverses for A. And try to show that actually, no, those two inverses are really the same. Yeah, that's exactly what we're gonna do, right? So let's assume that B and C are both inverses for A. So now we're getting some, first half of the class today was all crunching numbers, right? EROs and back substitutions and all that stuff. Now we're seeing a little more of the theoretical side of it. Okay, got a little bit of everything here. Suppose B and C are both equal to A. Well, then what are both inverses of A? Well, then that means that AB is equal to the identity is equal to BA, and at the same time, AC is equal to the identity is equal to CA. So all of these things would be true. Imagine that was possible. If that was possible, then what I'm about to do is I'm going to show you, I'm going to try to fill in the white space there and try to show you that actually B and C have to be the same. It's really clever. It's really clever. It just does not take much at all. Right, what I'm going to do, I'm going to start with B, and I'm going to just insert the identity matrix here. Remember, when you multiply by the identity matrix, it's like multiplying by 1. Yeah, so there's no harm in doing that, right? No harm in doing that at all. Are you able to see it? Oh, I'm good. Oh, okay. Just making sure I can put this down. Okay, so that's the identity matrix. Now what I'm going to do, guys, I need to get the C into the picture here, but I can do that because the identity matrix can be replaced by either CA or AC. I'm actually going to replace it by AC. I'll take the identity and put in AC there. And you probably remember from last week, we talked about properties of matrix algebra, and one of them was that parentheses don't really matter here. I can actually move them. I can't change the order of anything, but I can move the parentheses so that they go with the BA part, right? And then what is BA equal to? Back to the identity matrix again, right? That's also up here in part of the given information. Look at that. Look at that. We end up with identity times C. But of course, the identity is like 1. So I times C is just C. Oh, there you go. Okay, so there is only one inverse for a matrix, if there is one at all. And this is how you would prove that. Suppose that there could possibly be 2 of them. And then what you do is you show that they were actually equal all along. Right? They were actually the same all along. B equals C. I actually think that this line right here is the solution to one of the homeworks. Oh gosh, well, it's like 2 homeworks. We're like 2 homeworks ahead right now. Like we're working on material that's not going to be till next week. But you might see this again when you look at some homework from section 2.6. Yeah. Anyway, awesome. Because there's only one inverse, we're going to change our notations now. And we're going to write the inverse in a very a special way. So this is just a quick point of notation here, guys. The inverse of A is going to be written A to the -1 power. So if there is an inverse at all, we're gonna write it that way. We're not gonna keep calling it B or C. We're actually gonna write it with the suggestion that it looks like an inverse of A. Okay, and so what you now have, that what that means then, guys, of course, is that means that A times A inverse is equal to the identity matrix, which is equal to A inverse times A, right? So that's now kind of replacing what this box had said originally. Now, instead of this sort of abstract B that we had originally, now we have a notation that maybe at least mathematically looks a little nicer to us. Okay, so that's the inverse of A. Okay. I know that this is very theoretical, and this next thing is a little bit theoretical as well, but I will be getting to the examples and answering the basic questions about this in just a moment. But I first want to just show you the application of this. Like, how do you actually use this? Well, in solving, I want to go back to this linear system, AX equals B. Right? And this is where, in solving this system, so let's just really get this back into our minds. It's the same thing we had down earlier, right? So we take our linear system, instead of the A sharp that we were using earlier, which is still valid, right? Remember, what I'm talking about right now only works if A is a square matrix. So I'm not trying to throw the earlier material under the bus, right? We still need all of that. What we're saying here, though, is if we happen to get lucky and our linear system has A as an n by n invertible matrix, right? Then I have an alternative way of solving for x. X is the unknown, right? It's the vector of unknowns. See, all I have to do, guys, is I have to multiply by the A inverse on both sides. So I'm going to put the A inverse onto both of the sides of the equation. So I just took what's in the box and I hit it with A inverse on the left of both sides. Be careful. I think I warned you about this last week, but I see it all the time, is that people will do this. They'll say, oh, A inverse AX equals, and then the B is here, and they'll put the A inverse over here. Right? You have to be careful. This A inverse, whatever you do on the left side of the equation, in this case, I've put A inverse on the left of the left side, then I have to put the A inverse on the left of the right side as well, right? So this would be inverted. This is the wrong order. I've got to put it in this order here to make it make sense. But what if I just managed to do? A inverse times A is just the identity. A inverse times A is just the identity, and the identity times X is just X. A inverse times A is the identity, and then the identity times X is just X. So my friends, if your linear system has an invertible matrix as a coefficient matrix, and I know we have to talk a lot more about how do we decide if A is invertible? If it is invertible, how do we find the inverse? Like, these are all good questions I have not answered yet. But if there's an inverse for A, we're going to be able to use it to solve for X, right? And actually, remember from earlier tonight, we said that every linear system of equations, depending on how the pivots would go in the ERO process, every system has either no solutions, one solution, or infinitely many solutions. I'd like to add a footnote to that now. The footnote is that if your system has an invertible coefficient matrix, then this is the right answer. And because we see the answer is here. This is not infinitely many solutions. This is not 0 solutions. This is exactly one correct answer for X. And so in that case, Yeah, this is a case where you have one unique solution. Oh, so that must mean that if the matrix is invertible, then if you do the EROs on it, you must get the pivots going right down the main diagonal. You can't have any free variables. You can't have a pivot going into the far right column, right? Those were these other scenarios, right? So in the case of an invertible matrix, you already kind of know what's going to happen with your pivots. They're going to go right down that main diagonal. That's pretty nice. It's pretty nice. Did I talk to you about the rank the other day? The rank of a matrix? No. So I'm off my game then. I'll just say it now. We'll write it down later. The rank of a matrix is just how many pivots are in the row echelon form. I thought I said that, but I might not have. It got lost somewhere between Nebraska and here. Anyway, yeah, so turns out that for an invertible matrix, you're going to have a full set of n pivots, right? There's going to be a pivot going in every single entry of the main diagonal. That's another way to kind of think about an invertible matrix. It's just one that if you did the EROs on it, you'd get pivots going all the way down the main diagonal, because that's exactly the scenario when you end up getting one solution. Okay, so anyway, this is all going to fit together, and we will write it all down later. I just get excited and I jump ahead a little bit. With the 5 minutes I have left, I just want to go back to the basics before I get too super stoked about all of this, and just ask a couple of basic questions, which we will not be able to fully answer now until Thursday. But just really briefly, here's two obvious questions that everybody's probably asking to themselves right now. Just two questions to kind of put on the plate, and this will help get us set up for Thursday as well. One is, given the matrix A, which is n by n, how do I know if it's invertible? Right, so that's one question. How can we tell if A is invertible? Remember, if there's no inverse, then you can't do this application, for example, right? So that's a question. How can we tell if A is invertible, just given the matrix? If it's not a square size, then we also don't have an inverse, right? So it would only be for a square matrix. And then secondly, how can we tell if A is invertible? If it is, how do we find the inverse? How do we find A inverse? So if it's invertible, how do we find the inverse? Obviously, if we want to do this application and solve for X, I'm going to need to know, well, what is A inverse? Right? So those are two really good questions. And what I'm going to do right now, guys, is I'm going to answer this question. I'm going to answer these two questions for n equals 2 only. That's because I only have 4 minutes. On Thursday, I will come back and give you a more general answer for any size matrix, but this is easy enough to just write it down, okay? So I'm going to answer these two questions for a 2 by 2 matrix, okay? For a 2 by 2 matrix, I can just write out its entries. Like, it's not that hard to just write A, B, C, D down into 2 rows like that. The first question, how can we tell if it's invertible? Well, it will be invertible. I'll give you the answer right here. If and only if it turns out there is an easy test for a 2 by 2. I wish it would work for larger matrices, but there is no nice formula for the larger matrices. But this is an easy one. Namely, if we take A times D, which is just the diagonal entries, and then we subtract the B times C, this should be not 0. Not 0. Okay? So that's going to be easy. I can give you 4 numbers into a matrix and say, is it invertible? Here's all you got to do. Okay, take AD, subtract BC, make sure that it's not 0. And then in this case, we can actually answer question 2 as well, which is what is the inverse of this? So what is the inverse of this 2 by 2 matrix, assuming it's invertible? Well, you're gonna see right away, out in front of the inverse matrix, I'm going to take a reciprocal of AD minus BC. I better not have a 0 on the bottom here, right? So in order for this to even make any sense at all, AD minus BC has to be not 0. Okay, now what I'm about to write down, I'm going to fill in the matrix. You're going to want to memorize this one. Okay, it's not that bad. What you basically need to do is swap the A and D. So the diagonal entries get swapped, and then the other two entries stay in the same places, but they pick up a sign change. So we put a minus in front of the off diagonal entries. And that's how you write down the inverse in that case. Really quick, because I'm just about out of time, but I would like to know, let's say you don't believe me, that this is the formula for the inverse of the matrix. How could you verify it and make sure that I'm not lying to you? How can we verify that formula? One more time. Take this proposal for the inverse, multiply it by what A was, and what should you get when you do that? What should you get when you multiply the A by the A inverse? You should get that identity matrix back again. So just to check this, I will do this very quickly. To just check this one, you don't have to really take a huge amount of notes on this, but if you take 1 over AD minus BC times this matrix that I just proposed here. And by the way, this 1 over AD minus BC is just a number. It's just it's just a scalar. You could put this scalar into all of the entries if you wanted to, but you don't have to. You take that guy there and you multiply it back into the original matrix that you started with, and you're just going to check it. So this part here, this is the A inverse. This part here is the A, right? And if you now just crank that out, I will get saved by the bell pretty much on this one. The 1 over AD minus BC stays on the outside. And if I just multiply, right? Remember how we do this matrix multiplication. The rows of the first matrix get dotted with the columns of the second one. So I get AD minus BC up here. In the upper right corner, it's BD minus BD, which is 0. In the lower left corner, I have negative AC plus AC, well, that's 0. And in the far bottom right corner, I have negative BC plus AD. So you just get that AD minus BC again. And as soon as you feed this reciprocal scalar in there, look what you get. You get your 2 by 2 identity matrix back again. And that's exactly what you have to get to show that two things are inverses of each other. Okay, I think that's about a wrap. Any questions on that? On Thursday, we'll talk about larger n. But for 2 by 2s, that's the whole story. Thanks, guys, for being here. Appreciate it. Have a good night. I'll be around after 8 o'clock if anybody's got questions or wants to talk about anything. See you then.